So let's move to a topic on strength design procedure known as the balance strain condition. So a balance strain condition is simply defined as a condition wherein there exists a simultaneous yielding of the extreme steel in tension as the extreme concrete fiber crushes in compression. So the significance of knowing the balance strain condition is for us to be able to establish ductility. Uh, okay, ductility considerations in the design of beams. And when we talk of ductility, it simply states a condition in which your failure will be gradual, and it is manifested by cracking and deflection. Okay, so in in uh, in a ductile design, we need to uh, know whether the beam is actually on the verge of failing. No, it is very important that the beam behaves in a ductile manner than in a brittle manner. Okay, so the opposite of ductility is brittleness. Okay, so ductility, we don't want our material to be, or our member to be behaving in a brittle uh, fashion, because when the beams fail in a brittle manner, this is abrupt. Okay, it is sudden without any sign, while ductility normally is gradual, and it manifests, okay, some signs that is going to fail, and we want that because we can still make some remedies, okay, and save our lives. No, so if you want to abandon the beam or the area, we can easily we can still go out of the area when it manifests gradual failure. Okay, so how do we now uh, uh, consider the design as to whether it's ductile or not? So we have to understand the balance strain condition, which is a very ideal condition that sometimes does not happen. So here is the balance strain condition. Definition is on the simultaneous, okay, yielding and simultaneous crushing. Okay, so if I have a beam here, so this compression side, and this is the tension side, if this is the neutral axis. Okay, the fibers here are actually crushing, while the fibers here are actually crushing in, sorry, here is crushing in compression, while the fibers here are subjected to cracking in tension. But if there's a steel here, the steel will actually carry all the tensile stresses such that yielding, okay? So in this side there is yielding, and at this side there is what you call crushing. And this simultaneously reaches its ultimate value as assumed by the ACI, which is 0.003, and epsilon y is normally obtained again from the formula Fy over Es. Okay? And again, simultaneous occurrences of these two is an ideal situation. Ang hirap, mahirap siyang mangyari na sabay. That's why we have to find out where's the area wherein the behavior will still be ductile or ductile. And where's the area wherein the behavior is still brittle. So we don't want brittle behavior, we want a ductile behavior. And the purpose of determining this condition is to impose the limits of ductility on your AS or your rho. Okay, so AS is the steel area, and rho is simply the steel reinforcement ratio. Okay, which is given by AS over the effective area of concrete. Okay, so this is effective area of concrete. So let's now look into the picture. If we have here now a ductile behavior, where is the brittle behavior? Okay, so always the marking line will be your what? Balance condition. So this is the balance. This is the balance. So when your strain diagram falls outside the balance condition such that your epsilon is greater or equal to epsilon y, so meaning to say that if this is epsilon y, your epsilon, so this is wrong, your epsilon s is greater than epsilon y, okay, you have a ductile mode of failure. Okay, if we do that, normally you will see that your C here, if this is C balance, your C will be less than C balance. And vice versa, if your neutral axis on the balance condition is made in such a way that your epsilon is less than epsilon y, okay, so this is less than, then you have a brittle behavior, okay, which states that your C now, your location of the neutral axis is equal to the location of C at the balance condition. So that is the range at which ductility and brittleness is actually separated. But of course, we have some minimum, okay, so imposed here, minimum value, and we also have this is your maximum value for ductility. So we will be interpreting or analyzing that later in terms of the area. Okay, now this part here is an old exam lecture, so I will skip this. So it's up to you to study it if you want. So let's now go directly to the ductility provisions of the code itself. So ductility is the ability of a member to undergo large deflection before failing. And the modes of failure for a beam is the brittle mode with an I and the ductile mode. Okay, so this is sudden and abrupt. This is gradual. Okay. So for a ductile mode, the steel yields first before concrete reaches its ultimate crushing strain 0.003. So it's no longer a balanced condition because there's no simultaneous yielding, but what happens is that steel will yield first before concrete crushes. Okay? A brittle failure is the reverse. The concrete crashes first before the steel yields. Okay, so we don't want that to happen. So ductility may be controlled now by the amount of steel area. Okay, so this is area. AS balance, equivalent to the balance strain properties of the section. And if we recall the stress strain diagram of the balance condition, so what we derived a while ago. So take note of what we have on the equation for the ratio and proportion. What changes, napalitan lang ito ng C instead of having a this small letter C. A C, naging CB siya, no? So, small letter C yan. Okay? So, by taking the proportion of this triangle again, small triangle, and the other okay, the other triangle is this one. Okay, so this is 0.003 there. Okay, so 003 over CB is equal to 003 plus epsilon y over d. Okay, so we have here our equation. Our equation for epsilon y is given. So they are just the same. And then we'll yield to the value of CB, which is 600D all over 600 plus Fy, when we substitute ES is equal to 200,000 megapascal. Okay, so the value of C now, we're talking of small c here, no? At the balance condition, sorry, this is the value of C at the balance condition, and this is the value of A, the balance condition. Okay, so we simply make use of beta 1. What is beta 1 again? This is the Whitney parameter, stress block parameter. A. Okay, so in this case, it's A balance. Okay, so this becomes A balance. So from the stress diagram, C is equal to T, equilibrium condition. We now get your AB on the basis, ASB on the basis of all the balance. So this must be balance, balance. Because we're on the balance condition, you just make sure you have a subscript B there. So AS balance is equal to 0.85 FC prime. This is not the width, no? See, this is subscript. So AS balance 0.85 FC prime beta 1 CBB. Okay, C balance, and then this is the width all over Fy. And if we define a variable m on the basis of these two, so such that we are capturing now, we are capturing this part of the equation, okay, in this one. So this is the reciprocal of this, so we can put it at the bottom, m. So this becomes beta 1, and then we substitute CB, which is 600D over 600 plus Fy as derived here on top, okay, and B there. Okay, so it becomes beta 1 CB times B over M. Okay, so this is now your ASB, and we define a raw balance is equal to ASB over BD. So we divide this by BD, we divide this by BD, MBD. So cancel mo yung B, so magiging beta 1, cancel din yung M. Okay, no, sorry, your D cancels, B cancels, this is becomes raw. Beta 1 over M, 600 plus Fy is what you call the balance steel ratio. Okay, note for ductile design, Fy is equal to Fs. And we know that we can insert a factor of safety, let's say 1.33, to make it 0.75 raw balance. So that's the factor of safety given on the raw balance to get your raw max. So this becomes now 75% of this value here, and you call this now the upper limit for the steel ratio for rectangular reinforcement, or simply this is the maximum steel reinforcement or steel reinforcement ratio, or you can simply call it the maximum steel ratio, no? So you can omit the word reinforcement. So for the mode of failure, please take note of the ductility consideration. We always see to it that when your raw actual is greater than raw B, or raw B is less than raw actual, you get a brittle failure. We don't want this. What we want is a ductile failure. Okay, so what is the transitional ductility? So without a factor of safety, raw actual, raw max must be less than raw actual, okay, must be less than raw balance. Okay, so this is on the transitional region. Raw minimum less than raw actual less than or equal to raw max is the ductile failure. So we want this, okay? And raw actual less than raw minimum again is a brittle failure. We don't want this to happen. And this is a transition stage. Sometimes we can allow this, but it's better if we have this as your condition to make a ductile mode of failure. So what is the raw minimum? Raw minimum is the limit of raw given by the formula 1.4 over Fy, or but not less than this is equal to 1/4 square root of Fc prime over Fy, but not less than, or sorry, but not, yes, not less than 1.4 over Fy. Okay, so this is in mega Fy, and Fc prime must be in mega Pascal. Okay, so that is now your ductility conditions that we need. So let's have a problem here. Okay. So I think there is something wrong with whichever is greater. Okay, so safe to say that this is uh, let's change the notation there. Let's just place here whichever is okay greater. So it's hard to compare which will be less than. Okay, so let's change the quotation here. Okay, so let's put it whichever is greater. So whichever is greater, yun ang gagamitin natin. No? So raw octal now is equal to AS over BD, and this is only good for, remember, for rectangular section. Okay, so we're going to solve a problem on this on the next video. Okay, so let me end my lecture at this point.